And I think we're all good. So you could take it away, Joan. Thank you so much.
Thank you so much, Gabby. Thank you for hosting this webinar and organizing so much of it, and for everyone that is attending. I hope it's informative to you and it's part of an ongoing conversation that we have. I got to make sure I can advance slides. Okay. There we go. Very briefly, I'm with J.L Richards. We're a nearly 400
My students are
staff.
boring. They don't interact very much.
There's someone with that has a mic on that needs to be muted. Thank you. We have offices across Ontario, and we cover multidisciplinary engineering, architecture, and planning services across a number of different markets, and have an employee-owned company that's been in the business for more than 65 years. On this particular project, we built a multidisciplinary team that included energy staff, GIS staff, civil, and mechanical staff. And it was a wonderful group of people to work with. It's fun to get involved in something that's a little bit new and different to everybody, and pulling our knowledge and resources together on such a project. I'll now turn the table to Janice briefly to introduce some of the context behind this project.
Yeah, it was a pleasure to work with the J.L. Richards team on this. So just a bit of background, this what we were calling the waste heat study, or what became the waste energy transfer study. We identified that it was identified as a priority under our energy evolution strategy, which is our roadmap for how we achieve Council's net zero targets. Back in 2020, Council unanimously received and approved this strategy. It sets the framework for how we achieve those targets, both internal to the city and external, so corporate and community emissions. And it identified 20 projects that are to be completed within the next 5 years in key areas, including land use, buildings, transportation, waste and renewable natural gas, and electricity. Now, this project kind of spans between buildings and sort of waste, and how it supports a few of those objectives. Go ahead to the next slide, Joan. Thanks. So our strategy really mapped out how are we getting from today, or business as planned, which is the line if you follow across the top of this graph, to our net zero target by 2050, and how do we do that by also staying within the international carbon budget that's been agreed to at the Paris climate meetings or climate accords. So this is really our breakdown within the 5 key sectors of where those emissions reductions are going to be coming from. You can see the big green one there is existing buildings. And so we're looking at all ways to, and for a cold climate environment like Ottawa, and probably most of you, most of those emissions come from heating, from natural gas heating. So we're really looking for alternative solutions to zero emissions heating options for those existing buildings. And we looked at this wastewater energy transfer technology as one of those solutions, both feeding into specific buildings or into district energy systems that would serve multiple buildings. So I think for context, it's back to you, Joan, and I'm happy to chime in if anyone on the call has questions about from a municipal perspective on how the City of Ottawa is interpreting this data and planning to use it. We're at the beginning stages of that, but I'm happy to have a chat with you either in the chat function or perhaps offline as we go through. But this will mostly be a review of our survey, and we'll be hearing from Joan for the most part.
Thank you so much, Janice. Yeah, it's been a pleasure to do this project for the city, and just overall the work with the energy evolution team. This is a very comprehensive strategy, and a lot of things that they are tackling. They've made a lot of progress over the years, and we wish them and support them in all the moves forward that are still required to be done. So one further acknowledgement is that this work was funded by FCM, and we're very grateful for that. It allowed it to be relatively comprehensive, although still, as I'll say later on, we're still getting to know all of the details of this, of technologies such as this. For some context, there are sort of 4 different ways to capture heat or energy from the drains, and they're shown here in these 4 different diagrams. The first is a very simple device on the drain recovery that allows you to preheat domestic hot water, or the water going into your domestic hot water tank. The next stage up is capturing the wastewater just at the exit of the building. So it could be in the entire building, and that may be doing the similar function as the first, or can also be used for space heating. And there's some newer technology that would do space cooling at that level as well. The next level up is to actually tap into the wastewater that's flowing through the sanitary system and the sewage system. And the fourth is to actually capture the effluent from a wastewater treatment plant. And that, of course, is going to be your largest supply that can supply the plant or buildings or district energy system. There's a lot of different names for this technology. There's sewer waste heat, there's wastewater and sewage transfer. There's all sorts of different things. I just wanted to sort of specify this to some degree. At the smaller end of scales, you can use the term drain water heat recovery, especially when it is just heat that's being recovered. I'd like to encourage the industry to shift to wastewater energy transfer. So for the area that we're looking at, in particular, today's project is focusing on at the municipal lines across the city that are going to feed a building or district energy, and they're in fact able to provide both heating and cooling. So the motivation behind this is a heat exchange with a flowing liquid is one of the most efficient ways to exchange heat. And we're doing it with wastewater, which is warm in winter, around 10 degrees, and cool in summer, around 20 degrees. So those are temperatures that are much more moderate than, for example, an air source heat pump, which is trying to draw heat from below zero temperatures of the air and pump it back into 30-degree plus air in the summertime. So it's quite a high efficiency heat pump, and it is available for both heating and cooling supplies to buildings and district energy systems. We're motivated to get into this work because the resource is in fact large and also very well located in terms of the fact that it's largest within the urban core. The main alternative solutions would be air source heat pump, closed loop ground source heat pump, open loop ground source heat pump. It is a heat pump technology, as I'll get to in just a second. I'll give you a diagram, but here's some more of the background. In terms of heating operational costs, we've always sort of been told that natural gas heating is the cheapest and anything electrification is going to cost a lot. That has been true in the past, especially when older heat pumps did not perform very well in the Canadian climate. But with carbon tax, the cost of natural gas is rising. People are maybe just starting to see that on their bills this year, actually notice it. By the time we hit 170, this is assuming that the federal Liberal government's intentions to raise the carbon tax to $170 per ton by 2030, which is what they have announced. If those are realized, then the cost of natural gas will double in this time frame. So heat pumps soon start to become slightly more efficient, and their actual cost to operate depends on two important factors. One is the coefficient of performance, or how efficient they are, and the second is the cost of your electricity. So between these two curves, you can look at how the coefficient of performance can affect your cost to heat. So an air source heat pump is more likely to sit around that green line, while the orange line is more likely to be ground source or wastewater energy transfer system. And it's even better if you can tap into the Class A global adjustment rate scale, where you're often paying for cost of electricity at a 4 cents level. Okay, so the outline of this talk, the main aim, I'm going to do a technology overview of the different options that are here for wet systems. Look at how the wastewater is a resource for heat. Talk about how this gets implemented into some projects, and then some final thoughts and recommendations. I really want to point out to the fact that we're still essentially in a discovery process, all of us that are here around the table, in terms of how this technology will work. Does it pay for itself? Does it work well? Are there any downsides and any implications? Everything's looking promising and can come together pretty quickly. But to a certain degree, this is still a discovery process. So the presentation is based on the lessons learned primarily from this project. Our understanding may evolve, and the industry's understanding may evolve. And I encourage, if we have some time, that some of the people on the call may know certain pieces better to contribute or provide any corrections that do come through on this talk today. I'll leave it there. Okay, so the technologies. The main components are as follows: a heat exchanger that's drawing heat from the wastewater or injecting it into it, a pump to pump a working fluid through a loop of these connection pipes, and then a heat pump, which is actually turning that still relatively low temperature working fluid into a hot temperature suitable for heating a building. Some systems will also have wet wells and filters, as you'll see in a second. So this is technology one, which we'll spend a bit more time having a look at. And it's an actual heat exchanger. And I use the short form HX for heat exchange component that is actually inserted into an existing sewer line. It sits down on the bottom. It's designed to have a ramp at the start, I believe, and to be held in place through some ring clamps. It's going to sit through that sewage at all times. The intention is actually that there is some biofouling expected across that surface, and that decrease in efficiency of heat transfer is accounted for in the system. Because you're putting this in, it can be done potentially, I've been told, even potentially even with an active sewage flow, that it's relatively low cost for deployment. There are many deployments in Europe of this technology, and the main manufacturer of it, Irrig, is entering North America now with the technology. The second technology, the heat exchanger, is integrated into the pipe. And there are two companies that are out there that do this, and they're quite different designs. One is a wrap around the outside of the pipe, and the other is heat exchangers that are embedded into the cement of the pipe. PKS therm pipe and RAB therm. The real advantage of this approach is a zero interaction with the sewage. And so from that perspective, very low maintenance from a municipal city point of view. It's the most interactive with the ground. So it's the closest to actually being a sort of a horizontal ground source heat pump system as well. But it's going to have a lot of planning requirements around it. You're putting in a custom pipe. It'll have high civil costs if you're trying to do that ad hoc for a building without it being already part of the civil infrastructure work. So the other side of it is there's a lot of logistics to figure out at the right time with a build. Probably it would be a new build. At the moment, we are not aware of any installations that are in North America for either of those technologies. Technology number 3 is an external heat exchanger. And there's two main companies that are around and active in Canada developing these. In this, the sewage is borrowed from the wastewater pipe, brought into a wet well. So this is one company's wet well, this is the other. And both technologies involve getting the fluid to flow into a heat exchanger. Well, the solids are managed through, in this case, it's some filters down in the wet well. In this case, it's macerator plus filter system. The end result is the brown liquid is running through a heat exchanger, which then couples to your heat pump solution. So the heat exchange technologies are slightly different. Both have a degree of cleaning in them. This one is a mechanical clean of the pipe of heat exchange coils. This one is a backwash approach to it. In both these cases, it's a very proprietary heat exchanger. As I said, the integrated cleaning. Because of this approach of taking it away from the sewer line, the designs are allowed to be optimized for efficiency. The relative impact on the sewer line is still minor. The sewage is borrowed and returned within a short distance. There is more manipulation of sewage, so there's going to be more maintenance, more operational costs, and a higher footprint of doing that. But generally, it's very scalable as well. You can, especially on a big line, you can draw a lot of sewage into a large wet well and have a very large heat exchanger on still relatively speaking, a small footprint. They can even be integrated into the pump stations of a wastewater infrastructure system. Okay, so There's two main Canadian suppliers, Noventa, working out of Toronto. They're the exclusive supplier of the German manufactured Huber heat exchanger. And there's the Shark company out of Vancouver that their technology is Canadian developed. They've both done some really large projects and are both, I think, pretty active at developing many more. So these are two of the things that are out there. Toronto Western Hospital has been in the news recently. It's 8.5 megawatts of heating into that large complex. Vancouver Falls Creek is the oldest operating wastewater energy transfer system. It's been converted, I think, within the past few years to a Shark 3 megawatt system, and it's going to be upgraded to 8 megawatts now or in the very near future. Okay. So here's some key comparisons, and I broke it down to technology 1 and technology 3. There's similarities, but there are also really some differences. So there's a minimum sewage flow rate that makes sense for the technology to work. Technology 1, you can see, works better on a smaller system. So there's a smaller flow rates, smaller pipe system that you can put it in. That heat exchanger is going to be about 100 meters long along the sewage line. It's going to be able to deliver kilowatts worth of heat and a small footprint within a mechanical room. So it works well for the small to medium size flow rates and systems and heat delivery, whereas technology 3 works better at the larger sizes. There's more mechanical room required. The civil costs really sort of make it too expensive to do at the very small scale, but it works quite well at the medium to large scale. I want to emphasize here, these are very rough characterizations, just for some guidance to give you a feel of how this fits together. It depends very much on what you're assuming within the cost of a project. Civil costs can vary a lot, but the bigger the system, the more fixed civil costs you can fit into things as well. Okay. Moving on to the second main topic, which is the wastewater as a resource. How are we actually drawing heat from 10 degrees? Well, mostly the heat pump is doing that pump up to a higher temperature. The heat capacity that actually exists in a flowing liquid is a very simple equation. In fact, it's flow times the specific heat capacity of water times the temperature difference that you are affecting on that wastewater. Okay, so the delta T is the temperature difference between the sewage going into the heat exchanger and the sewage coming out. Heat exchangers can often only get so far. Typically, that would be 5 degrees Celsius, especially for technology 3. So flow is the primary determinant of the heat capacity of a wastewater line. The temperature and the sewage that's arriving there, it's going to vary hourly to a certain degree, as the flow varies hourly as well. And the temperature out, we do want to make sure that if the temperature is too cold coming in, that you may not be able to draw as much heat away from that sewage, because you want to stay away from the freezing markers and actually affecting flow in the wastewater system. So within this project, we made an assumption. It's not vetted or scientifically researched, but it generally makes sense to stay above 5 degrees Celsius. Detailed design could change what that number was, but it was a good place to start for this indicative work. When those temperatures are lowest, that heat pump has got to work harder in order to heat your building. So there's an efficiency effect here, and perhaps a net heat out of the entire system to a certain degree, or more electricity in to get the heating that you need. So we had to do a scan across all of the city of Ottawa. Here I'm showing the major sanitary trunk lines, as well as where there continues to be some combined sewer lines with the more golden color here. And we looked at whether there was some measured data. We looked at a lot of different measured data, and these were the types of things that actually did work within the context of the project. So there was some ETS, which is just environmental, I forget even what the acronym is, but it's basically just a flow monitoring system, that device that's set up at various points across the city. These are, we did a bit of analysis on those. And then these are 3 points that were embedded, that were flow and submersible temperature probes. I'm going to talk about those ones first. They turned out to be golden data sets. These probes were part of the University of Ottawa CO COVID-19 wastewater study that you may have heard about in the news. An amazing project that's monitoring COVID levels in the community. And nice scientific equipment that created an upside for us, that we got these really good data sets. So it was coincident temperature and flow that was useful for us. It spanned an entire winter, and the submersible temperature probes were really valuable to us for their accuracy. I'm going to show you what some of the results came out of these 3 lines. So I'm showing all 3 different data sets on top of each other here. The top 2 graphs are temperature. The left side spans the entire winter season, and the right side is a zoom in on 2 weeks. So it's really amazing to look at this temperature and see how consistent it was at those 3 different locations. Whereas the flow, of course, naturally would be different. One of the systems, the blue curve here from acres, is about 6 times higher in flow. So I've scaled that on the right-hand side, but you can see how consistent the patterns and trends are still at that higher flow system. A couple things I wanted to point out here, on top of that general trend consistency, is you can see where there are dips in temperature and increases in flow. That's where there's a rain event, a stormwater rain event. So the temperature does drop with December rains or December melts. And again here with spring melts that occur. And you can see the temperature, the flow definitely being much higher. Can anyone recall from that equation I showed before which way the heat capacity will go in this equation? I'm going to show the next graph in just a second, which is the equivalent heat capacity calculated from those things. Okay, so flow is the dominant factor in these 2 things. So in fact, the heat capacity that's available in that flowing liquid is higher because of the flow, even though the temperature's dropped a little bit.
Joan, just one question. I thought we'll just let me know if this is the appropriate time to ask it. But are there any worries with the heating of the wastewater that the sewer line would act as a digester and produce methane in the line, and any concerns with regards to pressurizing the line and flammable gas?
I would turn that to. Let's hold that question.
Okay. Yeah. No problem.
Whether,
no problem.
The
Totally
civil
works.
expert can answer that one. It is outside of my wheelhouse.
Perfect. We'll get to it in the Q&A section.
That sounds great. Okay, so I think I'm done with that particular slide. We're really interested with how you can also see this daily flow pattern that occurs with all wastewater. There's a morning rush and an evening rush and a nighttime low. And that happens day after day. The blue curve, as I mentioned, was the highest flow rate, potentially has the smallest variability across that, but the trends are still relatively similar across all 3 of those. Okay, you can take this data, which is hourly data across a season, and reorganize it from the highest point all the way down to a lowest point. And that's what this curve does. It's a heat capacity curve of that wastewater line. That can be useful for some design work to understand. You can very easily pick off what the minimum heat capacity is down at the bottom here where it intersects. And you can also see, well, a good part of the season, if you're okay with it getting it some of the time, there's actually quite a lot more heat available in that line. So that's really different than heating with natural gas, where you put in a boiler and then you can turn it up or down as much as you want. With the heat capacity here, if all you need is a trickle out relative to the sewage line, then you have as much as you want for your building. But if you're trying to work at a heat draw that's somewhere around here, well, you may not always have that. So this is going to come into the design discussion. Hold that thought. I just wanted to tell you a bit more about the flow measurements as well. Across the city of Ottawa, there were more than 600 ETS flow measurements, but they're often in short time spans and mostly in the spring and summer, when the city cares about peaks in the flow lines, and they want to check that the system is capable of handling the high flows of spring rain and spring runoff. Even 600 data points is still relatively sparse for a whole system as well, and they span a long period of time over the years, so they weren't all coincident. So although we at first thought that'd be very useful, they had some limitations in terms of being able to characterize the system or look at something. But the city does use those to calibrate their flow models. So we concluded that the city's flow model would typically be the most available data set to use for system-wide analysis. So it's a modeled flow variant, a model variant of the flow. It is, however, only indicative. You're going to see why in a second. In reality, through either these measurements or the one I saw, we saw some differences in the flow values between different, actually, sorry, I'm getting ahead of myself. Within the modeling, we received two different models, and there were some flow differences between those models as well. And the hourly patterns for a wet project will matter, but they did vary. They vary across the whole city. You can't just say, here's exactly the flow pattern. Back here, these are some relatively large trunk lines that they had a fair bit of consistency, but the average to peak value does vary, especially on some of the smaller lines. And that may matter because that will affect what's the minimum here. So, for example, for those 16 sites that we did look at, the difference between the minimum and the average was different at those 16 sites, between 20% difference and 65% different. To actually do feasibility in a real project would take, in my opinion, doing real measurements of temperature and flow to really understand what's available in that wastewater line. So here's a comparison between where we did go ahead with getting modeled data versus the measured data. You're familiar with the left-hand side already. The right-hand side is one of these, but we synthesized it to avoid the wet conditions. So we called it synthetic temperature profile. The one point I didn't mention, of course, is you can see the seasonal drop happening in temperature of the wastewater across the winter. What's a point about this is if you look, when your peak heating season is January, February, that's not your lowest point. Your lowest point in the temperature of the wastewater is down in the spring, March, April, in your shoulder season. So the flow model that we received is a single daily 24-hour profile that we repeated. And then you can convert that to heat capacity. So you can see there's still quite a lot of differences between a modeled value and a real measured value. If you just care about the minimum and you're going to stay under that minimum, it may not matter that much. Okay. A couple last thoughts on variability of temperature across the sewage line. First, we didn't actually get a chance to look at a combined pipe and the temperature and flows, but our gut feel on this is that a wet system should work on a combined pipe as long as you're working with those dry weather flows. The other thing that happens is, to what degree, this is a big question, to what degree is there heat exchange between that flowing wastewater and its environment, in particular the ground? How do we know exactly what that temperature is or will be, or if there's impacts downstream of a wet project? Well, already the temperature is varying quite a bit due to existing influences on the inputs, such as the potable water temperature, how users use their water, and infiltration into the system. And then the flow along the system is going to be influenced by heat exchange with the ground, with any air that's in that sewer line, and even the pipe type. So far, in some little bit of research and talking with suppliers, the suppliers are reporting that the sewage temperature, if you drop it from a wet project, it actually does tend to equalize back out further downstream, even within a few hundred meters. We haven't verified that. It's a real open question in my mind. We'd like to verify that. And the other sort of open question is, in a dense urban area where you have a lot more shower water essentially running compared to the length of the pipe, will that wastewater that you can use be a higher temperature? those 3 measured points we used were all relatively suburban. So I believe more study needs to be done on these items. I'll note that the region of Peel has more than 40 temperature probes distributed across their system. It'll be really interesting to hear what they learned from that study that I believe is ongoing right now. The one interesting piece of data that we were able to achieve was looking at the data from the Ottawa's wastewater treatment plant at ROPEC. Going way back for a quick second to where it is in the city, that one interesting thing about the city of Ottawa is it's a single large plant that serves the entire municipality. So wastewater is traveling quite a long distance to get there. It's got a lot of time to interact with the environment from the west as well as from the east. This is the Greenbelt area. So most of the sewage from Orleans then passes along relatively few inputs to get to ROPEC. So the data set there from ROPEC was really nice because it's 5 years of data. The top graph is temperature and bottom graph is flow. And you can see there's not really spikes or drops in temperature that correlate with high flow rates from storm events. And I took that data and plotted it instead as temperature versus flow. And if there was a relationship, you'd see it in terms of a line or some sort of curve, but there really isn't anything. It's much more sporadic and based on other factors. So that's really good news, or good indication of good news, is that ROPEC is unlikely to be affected by small changes in temperature drops further back in the wastewater infrastructure. It should be relatively insulated from any changes and effects. This needs to be taken further to understand that better still. It's always important to understand that the wastewater system is not being impacted. Okay. My third tidbit of topic is about the principles of the design itself. Excuse me. So I'll start down here. I've already explained this, how the wastewater heat capacity is varying on an hourly basis, but is relatively consistent day to day. We're going to draw heat from that through a heat exchanger. This is, I guess, showing technology 1, through a heat pump and feed that to a building. Now, perhaps there will be a secondary heat supply as well. In particular, that depends on what the building needs. So here I'm showing a building that also has variable demand. So we're trying to match this variable supply with the variable demand, or potentially we're trying to match that. It depends on the relative scale of these two. If this building heat demand is all much lower than the sewage variability, then it doesn't matter. But if we're trying to match the two of those, it's very interesting to look at the hour by hour. And there's nothing wrong with thinking about a secondary supply into any sort of a sizable building. This could be electric resistance, it could be going back to gas, or this could be part of a district energy system as well that has multiple supplies in. Okay, we did a quick look at a few example studies, and 2 where we actually had some building models that we worked with to do this sort of hourly study and thinking about what's the capacity and everything. So those are the first 2 studies of this complicated table of 4. One was a MURB, a multi-unit residential building, and the second was an office. In both cases, we used older existing buildings. We had the models nicely available for those. And we picked some locations in the city where, well, let's give it a try at this location. Doesn't necessarily mean that the intent was also to sort of learn generally, so that any learnings of a particular location could potentially apply to some others. The other 2 studies here, we looked at some locations that were particularly of interest for some development opportunities. And in those cases, we just looked at the heat capacities. So the point of this table is to sort of look at how the flow rates of our 4 different systems and the technologies we chose. And I'll talk briefly about the outcomes here. So we did this MURB, we did it with technology 1, partly because it was very small flow rate. And the second one, we did it with technology 3 because it was a little bit higher. But in both cases, we're pushing the bottom end of what might be viable, right? We're trying, these are relatively flow rates, coming back to the first parts in the technology section of my presentation. In the case of the MERB, the total outcomes in terms of the sizing and the return on investment looked okay for this application. Whereas we were really stretching it down to the bottom end of the flow rate in this particular study, and it really was very questionable as to how you would get to it, especially depending on the civil costs and the distances and everything involved. But that's not to say that a higher flow rate won't work very well. The one other tidbit within this study was that it was an office, so it's actually, this is the model we used, and you can see that it's only being heated 5 days a week during the weekdays. So it was an old building. It's very leaky. You should only put in heat when there are people there because it's so leaky, but then you need some really high peak heating needs. So it's very hard for basically any heat pump technology to supply that. The building should really go through some retrofit measures and be controlled differently. And you might have a different outcome and it might work. Very quickly about the two others, the flow rates from the model flow rates really varied on this line here. There was a 10 medium-sized sewer line traveling through the city. You could get 1.4 megawatts. That's enough to heat a very sizable building. And so that looked okay. That looked quite interesting. And then a major trunk line at 400 liters per second, you're really cooking. You can really heat quite a, might be a decent contribution into the district energy system, or heat high square footage development, especially for a new development with low heat demands to begin with. So I should say too that the main focus of our project was on the heating season because it was primarily aimed at carbon reduction. We didn't get into the cooling aspects of things, but that brings a lot more value to the project as a whole. So that can turn this okay into good, and these things into good as well. It was just a bit outside of the scope to get into all of those details. So that's the comparison of the wastewater heat supply to the building demand in the two archetypes we did. As I said, we were pushing our limits too in terms of how much we wanted to draw out of those wastewater. And here's some of our lessons learned. I think this is the real thing that's useful here. Is those older buildings with more envelopes and peaky heating schedules are harder to support. And daytime occupancy is harder to support because you built something and then you can only sell the output from it 9 to 5 days a week here. But the capital investment is the same, whether it's those shorter hours or throughout the entire year. In general, system economics is complex. It's dependent on so many design factors, and I have a graphic that shows you that. The competitiveness of a wet system is going to improve when you include carbon pricing, when you're looking at newer buildings with good envelopes, when you're looking at higher flows or larger projects, when you're including cooling, and when you're including funding. And I think it's really fair for me to say this because there are a lot of different funding opportunities out there. We have to consider those in the economics of going for these low carbon solutions. So that could be federal funding. For example, there's quite a few different things. ACCA is accelerated capital cost allowance for private companies that are investing in clean technology. That can have a real benefit. And there's more and more that we hope are becoming available. Okay. This is the underlying graphic you're familiar with already. Here's some of the many factors that are affecting the performance and the economics of it. And so there's a lot of stuff that you dive into in detailed design to pick all of these things and design in order to get the most economic solution coming out of the bottom end. So the flows and temperatures we've talked about, I didn't get into it, but civil costs, how far are you running from the sewage line to the energy center or the building? what size of heat pump is the best choice? Should it be so large that it can cover all heating demands, or should it be mid-sized and have a backup supply, for example? Details in this working fluid pumping loop. A lot of details around the building itself. It's scheduled for heating, it's scheduled for cooling. And are we going to retrofit it? If we're going to bring cooling in, do you have to build in a cooling loop that's new and not there in existence? Does that count into the economics? It's just going to vary project by project where your boundary of what's included in your cost comparison should be. But it's really got to be done with total return on investment or life cycle cost analysis, not just capital cost and not just operational cost, but the whole package. I wanted to just contrast to ground source heat pumps, for example. Something to note is the wet supply. We know it's variable within the day. If you're trying to get, if your load is similar to the capacity of that wet system. Even in that case, I believe it could be mitigated by some thermal storage or even just natural storage in a building with good envelope or thermal masses. But the wet system is very flexible seasonally in terms of its heating load and cooling load. You can do any cooling to heating ratio that works within the economics. I wanted to compare it to other heat pump options. So there's my little table here. So there's the wet closed loop ground source heat pump and an open loop ground source heat pump. So I just walked through this. The variabilities are different between these three technologies. A closed loop ground source heat pump, you have to balance the heating and cooling over the season, or you're creating a net temperature change in the ground below. Open loop ground source heat pump, you're tapping into the deep aquifer, and it's actually quite similar to a wet system. The geographic distribution, not all are. A closed loop system can work nearly anywhere, whereas the wet has to be near a pipe of size, and an open loop ground source heat pump has to have a good aquifer underneath it. So each one of these has their own sort of challenges that can be overcome in many situations. But it's good to think about these three variants as you're starting to look at low carbon solutions. In the feasibility assessment, is it easy or hard to do? Well, you probably want to deploy sensors for a wet system. And for an open ground source heat pump, the only way to really figure it out is to employ a hydrogeologist and do a deep test well. Closed loop ground source heat pump is higher because you're going to have to put a lot of boreholes. It's a lot of drilling to do at the capital side. Okay. They can work well together, actually. You can do a wet and a closed loop, or some combinations of these as well might be a nice solution. Okay, I'm glad to be wrapping up. Last two slides. Thanks for bearing with me throughout all of this. Really, the wastewater has been an underutilized energy source for a long, long period of time. The wet systems, they're viable. All indications so far are that the impacts on the infrastructure can be low, and they truly can be a great option for net zero carbon buildings. I've really observed this over the past few years. I think others have too, that there's significant interest growing in this as an opportunity for low carbon buildings. The MUSH sector is involved in it, lots of municipalities, hospitals, whatnot. And there's third-party ownerships available with some of this as well. So I would recommend that cities do actually need to move forward with developing policies and processes that could support privately developed projects, that could support their own corporate buildings, and could be part of any district energy infrastructure that they also are looking to engage in. Coming back to what I said earlier, that we're still to a large degree in the discovery phase of all of this. How well does it work? What are your rule sets? What do we still need to know? I have one last slide that's got a long list of questions. So really, we need a lot more industry and municipal sharing right now. In the next year, there's some projects out there. There's some data being collected. I suggest some forums. Maybe next year's FCM Sustainable Communities Conference has a panel about this as one example. And FCM supported this project, and I would suggest that they need to continue to support many different projects at the moment. There are many different differences going on in terms of figuring out how to make this work and work well. And that's both on the study side as well as on the project side. Here's the long list of questions that remain about the flow. So this is a summary of kind of the things I've covered already. There's questions about the flow. There's quantification of the temperature issues. There's understanding of the project return on investment. And there's a long list of variables in there. If you're trying to do a design of experiment against that, that's a lot of different studies. Even just on paper, Gedanken type study, there's still a lot of things to look at in there. So it's pretty hard to come up with a simple, does it work? It's like, yeah, it works in many instances. Here's the details you have to work yourself through. And key thing is, what information should municipalities provide to potential private developers? This is almost a question I'm throwing out to the audience. Many municipalities, but not all of them, have enough of their system online that you can go in and look at what the pipe diameter is. That's not a bad place to start for knowing about the capacity. Modeled flow is typically something that is not shared, but maybe it is useful. Should they share the modeled flow or the modeled heat capacity? Who has temperature profiles, and how can we learn as a group from those sorts of things? And since it's really, really nice to have a whole year of temperature and flow data, are there some locations where municipality can move in advance of a clear project and start measuring in advance some of those key parameters to help move things forward? And then finally, what policies for development do work best? There's a few municipalities that have these getting started. I'll turn it back to Janice to talk perhaps on where the city's going to go with that. And then, I mean, the last thing would be to talk about ownership, but I'm going to turn it to Janice right now. If there's anything on this slide or the next slide you want to sort of elaborate on, and we pretty much want to see if there's any questions remaining.
Yeah, thanks so much, Joan. So this information the study has just been completed. So the city is still in the phase of kind of digesting it and figuring out what to do next. So we don't have any direct recommendations beyond what Joan has laid out, but I did put a note in the chat. I am curious to know if any other municipalities have provided or shared flow data, publicly. That's something that we're looking into, but no, so far it's just the diameter of the pipe size diameter, and we don't have we don't tend to share our flow data publicly, modeled or accurate. And the other thing that we're looking into is if we can collect temperature and flow data over another heating season. So over this heating season, in particular in areas where there is high potential for this kind of system. So based on the study, we've identified that more of the urban area is a higher flow, higher potential, and we have some redevelopment projects happening in that urban area where there could be an opportunity for this kind of scale of system. And so we're looking at preemptively collecting that data over this winter season, this heating season, to be able to inform potential developers of the opportunity. Those are some things that we're looking at for now. And my colleague Mike is also on the call here, and he's been chiming in on these discussions. So Mike, feel free to jump in here if you want. Mike's good. Okay.
So there was mention, I know that you asked the question with regards to flow rates. I just wanted to mention that J.L said that City of Vancouver will provide flow rates and pipe size if requested and available. I'm not sure if there was if temperature is also something that they're measuring and able to share. So if that is the case, that if you could just kind of chime in there, that would be great.
Yeah. City of Vancouver has been really interesting too to watch, because they've been ahead of the curve on this with their deployment at the South Falls Creek installation back at when they hosted the Olympics. That was installed at that point. So they've got quite a lot more experience than most other jurisdictions in Canada. And what they developed after having that first pilot project installed, they then came up with a policy for how the city would proceed with private developers asking for access to the sewer. So they have kind of a sewer access policy with regards to capturing thermal energy from the wastewater system. So That's something that we've looked at. So far in Ottawa, we're not sure if that's the direction we're going to head, or if we're going to sort of experiment with a pilot project first and then use that to define a more comprehensive policy. So we're sort of looking at it with both potential paths as an option. And we're also thinking about how does this affect our own asset management with regards to our, civil works for maintenance and operations of our or upgrades of our wastewater infrastructure. So like the sewer infrastructure. So how, for example, if we're relocating or doing some work, digging up a sewer pipe, for example, that may need maintenance, and that sewer pipe, should we screen that sewer pipe for its potential for this kind of resource in the future, and maybe put in, sort of make it wet ready, is one thing we're considering. Is that possible to sort of put in conduit, for example, to make it easier to then access that pipe in the future and not have to dig up the street again, for example? So these are all sort of things we're considering, and I'd be very open to hearing what other municipalities are doing with regards to to making both data available and making their sewer infrastructure accessible for private or public access, right?
And Whale just also mentioned that no temperature is collected at this point in Vancouver, but they also said that King County, Washington, and Denver both provide data as they are actively looking to promote connection to their lines.
Okay, great. Thanks for that. That's useful. Yeah, what I've heard so far in Ottawa is we have the diameter sizing available, but the flow rate we will make available only on request for specific locations.
And Joan, for the probes that you put in, were they COVID probes that you also were then able to piggyback on to collect the data, or was it specifically done for this feasibility study?
No, it was very much, we were piggybacking on the COVID study. The city of Ottawa had been already engaged in supporting and in deploying those probes. So we got the data from their work. Yeah.
And then if it wasn't for the COVID stuff, for the COVID probes, what would be the costs associated with putting those probes in for collecting the data on the temperature and flow?
I actually don't know the costs full in. I don't know if there's anyone, Shelton recalls what those costs or Janice did through the process.
Yeah, I can chime in a bit there. So there's a couple of different ways to collect temperature and flow data. Submersible probes is what we determined were more effective. The OTA logs, which are in the airspace in the sewer pipe, don't adequately capture the temperature of the fluid. They're affected by external conditions too much. So we do recommend collecting with the temperature, or the temperature and flow, simultaneously with the submersible probes. The city of Ottawa has some of those probes already. So to deploy them for this purpose, it was just a bit of time to put them in and then take them out 2 or 3 weeks later, or every couple of weeks throughout the heating season that we wanted to measure. That's sort of how we did it, was extract them every couple of weeks, download the data, and then redeploy them. So those temperature sensors, I believe, now Sheldon, tell me if I'm wrong here, but when we ordered some, I believe they were in the range of like $200 to $300 a piece, and then plus the time to deploy them. So it's not a significant cost, but it does take some, you have to do it at the right time of year, right, for it to be effective.
Yes, and the actual probes aren't that expensive at all. But I mean, there is a little bit of data collection and so forth, so it's probably more like in the $400 to $500 per unit.
Okay, perfect, thank you. And then Whale also mentioned that they can speak to the Shark technology. Their systems utilize the thermal energy, which is very consistent and abundant, and the bioreaction thermal source is minimal and inconsistent. Also, if the system is designed out of a treatment plant, the infrastructure required to get the thermal energy into the population does not pencil out. I'm going to leave it actually to Whale, if you could unmute so that you can speak to that a bit as well. But I'm also going to mention we have a hit list on our to-do list which is reaching out to Toronto, Vancouver, and Joan just mentioned Peel Region. So I wasn't aware that Peel Region is also advancing this. So we're also going to add them to the list to get what they're doing shared with all the other municipalities as well.
Yeah, and there probably are additions to that as well, or folks that are at various stages of this discovery process.
Okay. I'm going to just go back to the original first question just before. And that was related to, sorry, I'm just going to go back.
It's
with regards to
chemical and temperature impacts within the line. Sheldon, do you want to explain? Sheldon was the other senior engineer on the team with a civil background. You able to unmute and give a quick kind of comment? It wasn't our main scope, is what I'll say about chemical interactions.
Mm-hmm.
Sorry, the one question about the chemical interactions on the.
Yeah, just if there was anything that with regards to whether the wastewater and the sewer line would act as a digester, the heating of the wastewater and the sewer line would act as a digester and produce methane in the line, and could be a flammable risk. Was there, if there was any analysis to that?
No, other than I did respond to that in the text.
Oh, okay. Thank you.
Just that we're dealing with relatively small temperature fluctuations, and in comparative to the overall flows, we are dealing with relatively small flows compared to the overall system. So, the 5 to 8 degree temperature rise in a small system, once it gets blended back into the system, isn't considered problematic. Now, in saying that, if we're dealing with dealing with all the flows and maybe some higher temperature differences, for instance, it would have to be something that could be looked at in the design phase, I guess, of the project. But overall, I would say no. Okay,
thank you. And then Mike also mentioned about, Mike, if you can just unmute just with regards to the hard building setbacks and how that relates to the question, because you mentioned hard building setbacks may be less optimal with a system with higher capital costs. That higher capital cost would just mean the extra piping that would be required as a result of the setback.
Yeah, I'm just, the sizing on a heating system for a variably occupied building is often sized for recovery from setback. So, if the system you're looking at is a little heavier in capital costs, then you might not drop your setback temperature down so much as part of the design, and that way save some capital on building the system. Or that could apply to maybe if there's a sewer limit that you're worried about. It's just be a design. I guess it's down the road, but would be a design consideration. And just I mentioned it. Just you don't want to hem yourself in at the early stage, and keep your options open. And so perhaps settling for a bit smaller system and not setting back as hard could be another way to optimize.
Right.
And then I have a question I'd love to ask about. You mentioned that cooling wasn't factored in. And I was just wondering, just on the back of the envelope, sort of thinking at this stage of the game, if cooling is brought into the kind of the feasibility and business case, wouldn't that improve the business case significantly because of the difference in efficiency between regular kind of, heat cooling systems and the heat moving towards a heat pump for the cooling purposes?
Yeah. There's two factors going on. Is that the actual energy transfer efficiency is very high in this system compared to, say, a cooling tower, and some of the maintenance may be lower as well. And as well, you're taking basically the same capital investment and using it through both seasons. So whereas the old-fashioned approach is a natural gas boiler system and a separate cooling set of cooling towers and everything. So you have to sort of factor in both of those business as usual costs against the single heat pump energy transfer system. And the overall package works really well.
Yeah, because I remember in the, say we're for feasibilities on geothermal systems, while the price differential in natural gas is cheaper, because of the fact of the cooling moving to a more efficient heat pump, that more than offsets the price differential between natural gas and electricity. So that's one of the reasons why I was curious about that.
Absolutely. It's very same story in this case, perhaps even more efficient on the cooling.
Okay, perfect. Are there any other questions, or did I miss any questions in the chat that weren't answered appropriately or clearly enough? You can always just unmute. No? All right. Well, thank you so much, Joan and Janice. I really appreciate you kind of taking the time to share Ottawa's work, all the work that took place in Ottawa with the rest of the municipal network. And all of this sharing is really, really important because it's new and emerging areas, and we really want to kind of learn from each other's experiences. So I want to thank you very, very much for taking the time and sharing this with everybody. And we are recording this, so I will be setting this up and putting this online, and then also sharing, sending that to you all in an email where you could then share that with others in your municipality or your community who you think will be interested or should be interested in this type of sharing and feasibility study work. So thank you so much.
Thank you once again.
And then I just see that I missed one question that came in. Oh, okay. Oh my goodness. So they have from technology option number 1, they have over 100 plants in operation in Europe. It's like one of those, another example of where we feel like, you know, hang your head in shame because we're so far behind where Europe is on this one. And sewer operators in Europe not only allow the installation of internal solutions, but also finance and operate the systems by themselves to sell energy to those buildings. So they've set up the utility model for buildings to opt into. My recommendation, make use of competition between different technologies. We installed plants with output from 50 kilowatts and 2 megawatts. Truth is, in many cases, you find relatively low flow rates. So go for all of the potential.
Yeah.
And it's another example when when you watch those Jason Bourne movies and you see the public transportation systems in Europe, and I always kind of hang my head in shame saying like, oh my God, it makes our public transit system look like so rinky dinky in comparison to the European public transit systems.